Hey there, Year 9s. In this video here, we're going to cover independent events, which we actually touched on our last session already with conditional probability. But here we're going to do a couple of examples just so you get a feel of it again. Okay? So independent events are when two events, like event A and event B, satisfy the following condition. And the condition is very key. This one is the cornerstone of understanding it. Now, it's always been done in Year 7 and Year 8, but it's been implied. It hasn't actually been mentioned. Why? If you remember, sorry, I'm missing a bracket there. If you remember the multiplication rule, back in Year 7 and 8, you would say that the A intersect B, the chances of A intersect B is actually probability of A times probability of B. You might not actually know that, so I'm going to draw a tree diagram to illustrate my point again. So remember in last session we said if I have a scenario where A happens first, so the first thing that happens is event A. So let's say flipping a coin or rolling a dice, whatever it is, yeah, or raining on day 1. So A happens or A doesn't. Then on day 2, so let's go day 1, day 2. Day 2, you can either have, again, now it either something happens or it doesn't happen. But notice here that it's actually not just B, it's actually B given that A had occurred first, because that's what this branch represents. Okay? But back in Year 7, you didn't actually see it that way. You saw it as this. So when I ask you, what is A intersect B, this is A intersect B, because that's the chances of getting A on day 1 and B on day 2. So that's essentially saying chances of getting A and B as one possibility, right? And so how would you have worked that out? If this was like 1/3 and this is 1/5, you would have said the probability of A intersection B is probability of A times probability of B. Now you would have done that in Year 7, and that's called multiplication rule. So you would have done 1/3 times 1/5, okay? But in Year 7, there was a key component that was overlooked, which is this bit. So the probability of B, it's not just B. This is actually normally, technically, B given that A had occurred. That's what that second branch technically represents. It's B given that A has occurred. What we don't know is that whether A has an effect on the chances of B. So we make that assumption. When you write B, you're assuming that B given A is just the same thing as finding B. That's saying, so that property right here, that when you're saying chances of A given B had occurred, so that means if B occurred first and then A comes after, the chances of getting A is totally irrelevant of whatever you get for B. That's why it's saying probability of A is the same thing as just A given B. Because A given B means, oh, I do care about what happened before, but then if it's just equal to A, then it essentially means it doesn't matter about what happens with B. Okay, so that's why we call it independent events. And that property there is very key, because that's what we're doing right here. So back in Year 7, technically, this should have been B given that A had occurred. That's what you were meant to be multiplying. But that's not how we teach it in Year 7, and we actually just write it as probability of B. But that's then assuming that they're independent. Okay, so if they're independent, that property there, probability of B, is actually equal to probability of B given A. That's a key property for this exercise. Okay? All right, so here it says, remember the conditional probability rule, and essentially I just covered it with you just now. A given B is probability of A intersect B divided by probability of B, okay? Or if you rearrange that equation, if you times both sides by probability of B times by probability of B, you'll find that these two cancel out, okay? And then you end up with probability A given B multiplied to probability of B will give you probability of A intersection B, which is very similar to the multiplication rule that we talked about up here. The only key difference is this bit. Okay, and so when I say logic here, I'm going to draw a tree diagram again. In this scenario, it looks like A given B. So it means B had occurred first. So B comes first. Then the second branch would then be A, not A, not A. So when we want to find probability of A intersect B, isn't that just this branch multiplied to, so this is probability of B, multiplied with this branch, which remember is not just A, this is actually probability of B given A had occurred. Okay, so, probability of A given B, given that B had occurred. Okay, that's essentially what it is. That's what that represents. And that's what I'm trying to say here. Okay, pause the video if you need just to have a think of what I just said there. So this is a conditional version of it. So this is saying probability A intersection B is probability of B times probability of A given B, based on the tree diagram I'm drawing. Okay, and that second line there, the given part, that's what makes the difference between conditional versus independence. Let's do an example just so that you get a feel of it. Say example 2, a selection of 14 hotel offers includes 8 with free Wi-Fi and 9 with a free breakfast. So you have Wi-Fi or you have breakfast, yeah? Whereas 3 offer both free Wi-Fi and breakfast. So let's summarize it in a Venn diagram. I'm going to draw a Venn diagram. Here we go. Here's our universal box. We got breakfast or Wi-Fi. We got 3 have both. And 8 with free Wi-Fi, so free Wi-Fi, that means this has to be 5, because 3 plus 5 gives you 8, right? So 8 has to have Wi-Fi. Whoops. Do it again. There we go. And what's the other one? 9 has to have free breakfast. So if it's 9, that means this has to be 6 for breakfast. Okay, but 6 plus 3 is 9. 9 plus 5 is 14. And there are 14 hotels. Okay, all right. So that means there must be nothing that fits within that. So there's no hotels that don't offer either one of those. So I've done my Venn diagram. And what do they want? Okay. Yeah, I've drawn my Venn diagram. Cool. Find probability of A. Now, I personally like, when you're doing calculations, use cardinal maps. So in this case here, I would have done breakfast, no breakfast, Wi-Fi, no Wi-Fi. There's a total of 14. 3 goes here. Total of breakfast was 9. Total of Wi-Fi was 8. And then just fill in the blanks. So here, 8 plus 6 and 9 plus 5. This is 6. That must be 0. And then 3 plus 5. There we go. So I filled it all out, right? So I've got my cardinal maps table. So now the first question is, what's the chances of picking someone is A? What's A represent? I'll let A be the event choosing a hotel with free Wi-Fi. Okay, so essentially it's asking probability of Wi-Fi. So Wi-Fi, how many people have Wi-Fi? Oh, hotels. It's 8 hotels out of 14. And that's, 4 over 7. Okay, so chances 4 over 7. That's pretty straightforward. Probability of A given B. Now, we know probability of A given B is the same thing as probability of A intersect B divided by probability of B, because B is what had occurred. Essentially, they're saying, what's the chances of getting Wi-Fi at a hotel, given that you know they give breakfast, free breakfast. So if you look at the diagram, if you already know they're going to give free breakfast, it's one of those 9 hotels. Okay, so out of those 9 hotels, what's the chances of picking one where you're going to have free Wi-Fi as well? So it's obviously there. So it's 3 out of the 9. True? Just logically, looking at the diagram there, I know the answer is 3 out of 9, which is 1/3. But say you didn't know that, well, you can actually work it out by finding the probability A intersect B. So what's the chance of getting Wi-Fi and breakfast? Well, it's 3 out of 14 people, or hotel, sorry. 3 out of 14 is the chance of getting Wi-Fi and breakfast. And then the bottom one is chances of getting breakfast. Well, we already knew there were 9 hotels out of the 14 hotels that had breakfast, free breakfast. And so if you work that out, that's 3 out of 14 divided by 9 out of 14. But when you divide fractions, you do the reciprocal, so it becomes 3 out of 14 times 14 on 9. 14s cancel out, and you end up with the same answer. 3/9 is 1/3. Okay? And what's the last example? State whether or not the events A and B are independent. Well, if you want to know if it's independent, it's very simple. The multiplication rule, which is the most obvious point, A intersect B should equal to probability of A times probability of B. If they're independent, this will be true. If they're not independent, that would not be true. It will then obviously have to be a conditional probability. We already know what A intersect B is. A intersect B was 3 out of 14 based on the table and diagram. So 3 out of 14. Now, probability of A was the chance of getting Wi-Fi. It's 9 out of 14. Oh, sorry, 8 out of 14. Oops, 8 out of 14 times probability of B, which is breakfast. Is it breakfast? Yeah, providing breakfast, which is 8 out of 14. Huh? No, breakfast was 9 out of 14. You can already see that 3 out of 14 cannot be true because 8 times 9 does not give you 3 out of 14. 8 times 9 is 72. So clearly, they're not independent. Cool? That's all you do. That's pretty much the exercise on 8G, independent events. It's again a nice additional exercise to conditional probability. I would recommend you to do conditional probability first, understand the theory first before you look at independent events because they're very, very similar. Okay, it's just the change of one of the probabilities. That's it.